famous politician once said that Britain was an island almost made of coal and surrounded by fish. Certainly, large areas of a country have a lot of coal not far below the surface. It was a neat way of saying that we as Britons need never be cold or hungry. Times were pretty tough then, but it was reassuring to be reminded that with hard work we could catch enough fish to feed ourselves and win enough coal from beneath the earth to heat our homes and run our factories. Well, over the years the fish stocks have dwindled. We have to share what's left with the other countries of Europe. But what is amazing is that we know now that there is more coal under Britain than we ever thought possible. Extensions to existing mining areas and some completely new coal fields have been mapped in a wide-ranging programme to discover the true extent of Britain's coal reserves. Coal. What is it, some of you may ask, especially if you live in a big town or city? It's not surprising that we don't see very much of the coal that's mined in Britain. Most of it's delivered in bulk to power stations or factories. You may catch just a glimpse of the coal as it's whisked on its way to a power station, 1,000 tons at a time. More than 2/3 of all the coal mined in Britain is burnt to make electricity. Most of the really big power stations are sited near to the coal mining areas that supply them. Coal for use in the smaller factories and for homes will be carefully graded and stockpiled, ready for delivery locally. Some of it's specially packed to make it easy and clean to handle. All you will probably see of this coal are the stacks of plastic bags outside the hardware shop, garage, or perhaps the greengrocers. Quite a lot of people use coal to heat their homes, but in towns we may have to use a smokeless fuel. That's coal which has been treated so that it burns without a smoky flame to help keep the town's air cleaner. Coal is a form of stored energy, the sun's energy. When the sun shone down on Britain millions of years ago, more than 250 million years ago in fact, it was helping to make the coal that we are using today. All those millions of years ago, things were very different in our part of the world. Where the coal fields are today were great swampy tropical forests, rather like the forests of the Amazon or the great rivers of tropical Africa are today. Dead leaves and fallen trees mingled on the swamp floor with mosses, ferns and water weeds. The mass of decaying vegetation gradually increased until, perhaps because of a great flood, a volcanic eruption or an earthquake, a river would change course, and where there was once forest became a huge sandbank or miles and miles of mudflats. All this happened many times over. As each layer was buried deeper, the weight of layers above and the heat of the earth below turned the decayed forests into coal and the sand and mud into rock. While the coal measures were being built up, and indeed ever since, the surface of the earth was moving, slowly but with enormous force. The layers of rock and coal were pushed from the sides so that they buckled, forming arches and hollows miles across. Often they would crack under a tremendous tension and great chunks would slide up or down. This is called faulting. Glaciers during the ice ages and rivers and seas in warmer times have cut into these folds in the surface of the earth, causing the layers or seams of coal to become exposed. Our ancestors often scavenged for coal on the seashore. They found it burnt well and stayed hot for a long time. But in those days, the forests of Britain were still huge, so for a long time there was no increase in the demand for coal. Wood was still plentiful and cheap, and the country's population increased only very slowly. In the 14th and 15th centuries, many of our great cathedrals were being built. Merchants and craftsmen were beginning to prosper and provide themselves with fine houses. Large quantities of wood were used in building these houses. So, around towns and cities, wood was becoming scarce and consequently expensive. Large quantities of wood were also being used for building great fleets of ships, for exploration, trade and war. Since railways hadn't been invented yet, and the roads were mostly still only fit for pack horses, the important cities of this period had grown up on tidal rivers or estuaries. So, when there was a market for coal, it came in by sea. It was, in fact, called sea coal to distinguish it from charcoal, which was made from wood. The increasing demand for coal led to more determined and sophisticated mining methods. The miners dug deeper into the hillsides and contrived ways to drain away water, provide a supply of air, and get the coal to the surface as quickly as possible. The other widely employed method of getting coal was the bell pit. We call them bell pits because of their shape. Bell pits were rarely more than 10 meters deep, the height of a two-storied house. Coal was taken until there was a danger of the pit caving in, then it would be abandoned and another started a few yards away. These small mines were often just family concerns, and the coal would be sold locally. Many different systems of mining were tried out as the coal trade developed during the 18th and 19th centuries. By this time, coke made from coal had largely replaced charcoal in the iron-making process. From now on, iron could be made and worked much more easily and cheaply, and in much greater quantity. Demand for iron meant demand for coal in the form of coke. For miners in those days, work underground was hard and dangerous. The only power underground was muscle power. Even children as young as 8 or 9 were expected to work 12 hours a day, every day except Sunday. Candles and crude oil lamps were still the only really practical means of illumination underground. During this period, there were 2 great obstacles to increase production in our mines: explosive gas and water. The first of these, gas, was by far the more dangerous. Mixed with air, a spark or flame can ignite it. Hundreds of men and boys, and sometimes women, died or were injured every year in the explosions and fires that resulted. But the invention and development of the safety lamp brought about the biggest saving of life in the mines. Scientists and engineers such as Sir Humphrey Davy and George Stephenson worked to perfect the safety lamp. This is one of the designs of safety lamp in use today. These days, its main function is to test for the presence of gas rather than give light. The flame changes size and color when flammable gas is present in the atmosphere, without the risk of causing an explosion. The other serious problem for miners about 200 years ago was water. With only horses to work the primitive pumps, flooding caused many small mines to be abandoned and made work impossible at many others during bad weather. Steam power came to the rescue. Thomas Newcomen's invention of the steam pumping engine revived the fortunes of the coal mines, allowing production to be greatly increased. Within a few years, the efficiency and power of the beam engine had been considerably improved. Machines like this one drained mines, pumped fresh water supplies to towns and cities, and raised water for canals, which by now were carrying much of Britain's freight. Horse-drawn narrowboats could carry about 40 tons of freight, but their average speed was about 2 miles an hour, a slow walking pace. The next great step forward in the Industrial Revolution that was going on in Britain was to link the power of the steam engine with the potential for speed and flexibility of the new railway. The coal industry would help to make that step, and again, in its turn, would benefit from it. The first steam locomotives were built for collieries and ironworks. This is an exact replica of an engine called locomotion. The original was built in 1825 by George Stephenson for the world's first public railway line, which ran from Stockton to Darlington in the northeast. The coal mines continued to prosper, supplying coal to run the rapidly expanding railway system, as well as coal to make iron for the rails. Now there were steam boats, too, that needed coal. Since the start of mining, coal was brought to the surface using horsepower. Usually only 1 or 2 horsepower. The horse gin, as it was called, was slowly replaced by steam winding engines, based on the old pumping engine, and later by the horizontal cylinder design. Steam engines wound coal to the surface much faster than horses could. But even steam was about to come to the end of the line. The introduction of electricity, both on the surface to power ventilation fans and winding engines, and underground to operate drilling and coal-cutting machinery, transformed the mining industry and made it what it is today. On the surface, not all mines look as modern as this, but they all use modern techniques underground to win the coal and bring it out of the mine. Let's see how it's done. This is the control room. From here, contact can be made with all parts of the mine, from the manager's office to the farthest working underground, by telephone, loudspeaker system, or sometimes radio. The condition of the atmosphere underground is checked continuously by automatic instruments, and the movement of coal along the underground tunnels, or roadways as they are called, and up the shaft is controlled with the aid of a computer. Often now, several mines will be linked together underground, so that the coal from all of them can be brought to the surface at the most convenient place. The control room may well be monitoring the underground operations over an area of 20 to 30 square miles. Remote-controlled video cameras help to monitor the performance of machinery in all parts of the mine. The coal travels right from the coal face to the surface on an endless belt, called a conveyor belt. We shall see a lot of conveyor belts underground, as they are the most efficient way of transporting coal. Quite a lot of mines have a drift, or sloping tunnel, so that coal can be brought to the surface without ever having to be loaded into tubs or wagons. Unlike those early mines, these drifts will be a mile or more long, sloping steeply all the way. Although coal can be easily transported over long distances on conveyor belts, materials, that is, steel girders, cement, machinery, and men, are usually carried down a shaft in a cage. Yes, that's what it's called, but it's really just a lift. This is the first stage in the journey to work for the many men who still have to work underground in the mine. After changing into workwear, which is a specially designed set of clothing issued to all miners, the next thing is a visit to the lamp room. Everyone collects an electric cap lamp and a self-rescuer. Inside this small container is a mask to use if there should be an underground emergency. It will protect the wearer from the fumes of an underground fire or after an explosion for long enough to get to safety. Safety is a top priority in all our mining operations. Everyone collects 2 tallies, numbered metal discs.
375.
One of these is given to the man in charge at the top of the shaft, who is called the banksman.
Check 261, please.
The other tally is retained by the man going underground. In this way, if there should be an emergency, it would be easy to check that everyone had been accounted for.
Help, Cupboard!
Let's follow them down below and see what mining is like today. As soon as the cage is full, the banksman signals to the winding engineman and the cage is lowered away. These days, the winder is driven by a powerful electric motor. Or perhaps even 1,000 meters below, the men leave the cage to walk to their train. The roadway near to the bottom of the shaft is well lit with electric lights in gas-proof housings. The mine is divided into several districts, with 1 or more coal faces being worked in each. The ride on this train will save time and effort getting to a working district perhaps a couple of miles away from the bottom of the shaft. The train is hauled by a powerful locomotive, and the engine is flame-proofed, like the electric lights in the main roadway. The layout of a typical mine will look like this. There are 2 shafts. The one on the left carries men and materials, and the other carries coal. The train takes men from the bottom of the shaft and drops them off at a point nearest to their place of work. Men working at the coal face will have to walk the last few hundred meters along the side tunnel leading to the face. This is what is called a long wall face. These days, almost all of the deep-mined coal in Britain is won by this method. The coal face is, in fact, a long wall of coal. The cutting machine takes slice after slice from the face, and it usually advances into the coal seam. This surface demonstration shows how the machinery works on the coal face down below. Hydraulic-powered supports are set along the length of the face, about 1.5 meters apart. They act against the pressure of the rock strata above the coal face. As it moves along the face, the shearer loader, as it's called, cuts the coal and pushes it onto an all-steel conveyor, called an armoured face conveyor. The roadways at either end of the face are excavated to keep up with the coal face as it moves forward. Ventilation of the face is provided by diverting fresh air along one roadway known as the main gate. In the main gate, another conveyor belt carries the coal away from the face. The other roadway, which carries stale air away from the face and serves as a second entrance for supplies, spare parts, extra girders and so on, is known as the tailgate or return gate. It can also be used as a second exit in an emergency. Here we are in the main gate, and these men are going onto the coal face to start their shift. The cutting drum of the shearer loader has dozens of hard steel picks fitted to it. The shearer loader is driven by an electric motor of up to 400 horsepower, rotating the cutting drum and driving it along the face. Water sprays around the drum cool the picks and help to keep down dust to a strictly controlled level. A second cutting drum is fitted to the other end of the machine so that it can work in either direction. Most long-wall coal faces are between 150 and 300 meters from end to end, so there may be up to 200 powered supports along the face. Behind the shearer, the hydraulic-powered supports are moved forward, pushing the conveyor into the space where coal used to be. The face will then be ready for the shearer to take its next slice of coal on the return journey. It's hard and skillful work, keeping this machinery on the move 6 or 7 hours at a stretch, so the miners are glad of a break in the middle of a shift. Snap time, they call it. While the men on this face are taking a break, the coal from other faces in other districts keeps on flowing out of the mine, transferring from one conveyor to another to emerge from the mine some 250 million years after it last saw the light of day. In addition to coal obtained by deep mining, some 15 million tons of coal a year, about 1/6 of our total production, is won by open cast or strip mining. Coal seams less than about 100 meters below the surface can be worked by removing the soil and rock, called the overburden, with machines like this one, nicknamed Big Geordie. Weighing nearly as much as a cross-channel ferry, its huge bucket can lift 100 tons of material with a single bite. As one part of the site is excavated, the overburden is transferred in a fleet of big trucks to refill those areas from which the coal has been extracted. When the operation is complete, the topsoil will be replaced, trees planted, grass grown, and the land restored to use. Most of the coal we produce, whether from deep mines or open cast workings, will go to a coal preparation plant. As it passes through the plant, a series of processes grade and wash and test the coal to ensure that customers get the size and quality they require. More than 2/3 of the coal mined in Britain goes to feed the power stations to make electricity. This is Drax Power Station in Yorkshire. It's capable of burning 10 million tons of coal a year, making it the largest coal-fired power station in Europe. This train, carrying 1,000 tons of coal, is called a merry-go-round train. They're called merry-go-round trains because they travel on a circular route from mine to power station and back, and are able to load and unload without stopping. This whole train of 30 wagons is loaded in as many minutes. For the foreseeable future, electricity generation will remain the largest single market for coal. Electricity from these large and efficient power stations is distributed throughout the national grid system to give us light, power the gadgets in our homes, run a large part of our railway system, and supply power to thousands of factories. But coal is now recapturing its traditional markets. Large industrial and commercial customers are converting from other fuels and returning to the use of coal for steam raising, to heat workshops and offices, and to provide energy for industrial processes. Coal traditionally supplied the country's manufacturing industries with energy. Millions of tons of coal a year are still turned into coke. Most of it is used to make iron in blast furnaces. These rotating kilns produce cement. The process uses the heat from coal. As an increasing proportion of our total coal production comes from new or re-equipped collieries working at high efficiency, the mining industry will steadily regain its preeminence in these industrial markets. Deliveries of coal can be made in different ways. It can be placed in bunkers or storage hoppers, precisely, easily and cleanly using specially designed road vehicles. Industrial water heating and steam raising units like this make use of the latest electronic control techniques to make the best possible use of the coal they burn. The coal is fed in automatically and the ash is removed automatically. The rate at which the coal goes into the furnace and the flow of air to make it burn, even the water and steam valves, can all be remotely controlled from outside the boiler house. In the coal fields, a number of companies use the explosive gas methane as a fuel. The gas seeps out of the coal seams and is known to miners as fire damp. For each ton of coal mined, about 6 cubic meters of methane gas is released, enough to run the gas central heating system of a 2 or 3 bedroom house for a couple of weeks. The methane is drained away from the seam before the coal is cut, another important safety measure in modern mining. New ways of burning and using coal are being developed at the board's coal research establishment. Fluidized bed combustion is one of the most important. It is making possible an increase in the market for coal as a fuel for industry. When air is blown into the bottom of a container full of a finely divided or ground up material such as sand, the mixture behaves just like a liquid. If the sand is red hot and the coal is fed into the fluidized bed, it will burn in the supply of air passing up through the bed. Chemicals can be added to the bed in order to absorb potentially harmful gases before they leave the furnace, to the benefit of the environment. Eventually, the system of combustion will be used on a much larger scale in electricity generation. Already, many fluidized bed boilers are in commercial use and many more are planned. For several years now, in this boiler house, a fluidized bed boiler has been working alongside more conventional steam raising equipment, which supplies a district heating scheme comprising hundreds of flats, houses, offices and shops. The local Olympic-sized swimming pool also gets the benefit of low-cost heating. Coal supplied the country with gas long before natural gas supplies were discovered beneath the North Sea, and no doubt will have to do so again as offshore gas and oil reserves dwindle. As well as being a fuel, coal, just like oil, can be processed to supply many different chemicals. Drugs, dyes, paints, plastics, fertilizers and explosives, all have been made from coal. There are some applications for which raw coal itself could never be used. But even oil can be made from coal. The process has been successfully operated in the laboratory, and a larger scale pilot plant will develop the process further, so that by the late 1990s, commercial scale plants will be able to turn coal into fuel for aircraft, diesel and petrol vehicles. The future success of these ventures will depend upon the mining industry's ability to meet the requirements of the energy market at competitive prices. Exploitation of newly discovered coal reserves make this possible. Sometimes this will be done by modernization and extension of existing collieries. The revolutionary design of these new headstocks is an example of the coal mining industry's concern for good industrial design. The Selby project in Yorkshire is a completely new coal field, about 100 square miles of thick, good quality coal seams. Designed by a team of engineers and architects from the ground up and down. All the surface buildings and equipment were carefully sited and designed to minimize the impact on the rural surroundings of this huge industrial undertaking. 5 pairs of mine shafts will be used to carry miners and equipment. They also provide air for ventilation of the underground workings. All of the coal is carried on underground conveyor belts. The main ones, more than 9 miles long, stretch right across the coal field. Coal can be brought to the surface at a rate of 2,000 tons an hour up this drift or sloping tunnel to a depot beside the main railway line. The loading machinery here can fill up to 50 trains, each made up of 30 wagons every day. Mines like Selby are enabling deep-mined coal to be produced efficiently and cheaply, to supply customers at home, and to allow Britain to maintain its exports of coal. Much of our coal which goes abroad these days is sent through the board's specialised bulk handling terminal at Immingham on the Humber estuary. A remotely controlled conveyor belt system allows a few men to pick up the coal from the stocking ground and drop it accurately into the hold of a large bulk carrying cargo ship. The search for coal goes on. Over a period of 10 years, even more reserves of coal were discovered by seismic survey than the entire amount mined during the same period. The new discoveries are explored from the surface by drilling rigs like this. Despite our long history of coal mining, the existence of an additional 1,500 million tons of high-quality, accessible coal was confirmed. Drilling was carried out at sea as well as on land. In the northeast, coal is already being won from faces 10 kilometers offshore and 300 meters beneath the bottom of the sea. These rigs enable geologists to take samples 1,000 meters or more below the surface. The coal prospectors make an initial inspection of the core, as it's called, and then send it off to laboratories for detailed analysis. It takes up to 10 years and many millions of pounds to sink the shafts and develop a coal field. And the engineers don't want any surprises when they eventually get down there. A comprehensive exploration program is still building up a detailed map of our island of coal. These geologists are taking a look at the future of coal mining in Britain. The task of Britain's high-technology mining industry is to meet the undoubted future demand for coal at the minimum possible cost. British mining has a long history. It can look forward to a shining future.